Rolling.
Okay. Not again. We accept. Okay, let's see if we can figure out where we left off. Yeah. Last time we were talking about transmission lines and several different configurations of transmission lines. What we're going to do today is to go over basic transmission line analysis and transmission line equations, which hold for all these different types of transmission lines that we've been discussing. Before we get into transmission line analysis, let me state for the record that we're going to be dealing here with time harmonic transmission lines. That is to say, we're going to be dealing with a case where the transmission line circuits are excited by sources that give us AC signals, sinusoidal signals only. We're not dealing with the general time varying case, like pulsed transmission line circuits and things of that nature. We're going to be dealing with the AC case, where we can make use of the nice mathematical simplifications that occur when you make use of phasors rather than time varying signals. Now, this isn't much of a restriction, actually. You might say to yourself, well, what happens if I've got a circuit where the source doesn't give me a pure sinusoidal signal at a single frequency, but instead gives me some sort of other odd-shaped periodic signal? Well, in that case, you can still use phasor analysis. What you would do in that case would be to decompose the signal in a Fourier series and then treat each component of the Fourier series as being a sinusoidal signal and use phasor analysis on that particular component of the Fourier series and do the calculations for that particular term in the Fourier series, and do this for all the terms in the Fourier series, and then say, well, the total signal exciting my system was the entire Fourier series. Take all those results I end up with for the result of each of the terms of the Fourier series, add up all of those results, and you'll get the result for the arbitrary periodic waveform. So, talking about the case that we're going to be considering here, a case of a sinusoidal excitation at a single fixed frequency of omega, isn't as quite as much of a restriction as you might at first think. In any event, as long as the circuit is a linear circuit, then if the source consists of a signal at a single fixed frequency, all the voltages and currents and any other quantity of interest in the circuit will also vary at that same fixed frequency. Now, we've already talked about the fact that in electrically large circuits, we've got to think in terms of traveling waves of voltage and traveling waves of current and things of that nature. Now, the mathematical expression for a traveling wave voltage, let's say, is something like what I have written up here. Some magnitude, constant magnitude V0, that might be 5 volts, times the sinusoidal variation. In this case, I'm going to use the cosine reference. I call it cosine of omega t minus beta x. Omega here is the given fixed sinusoidal frequency, radian frequency, by the way, radians per second, 2 pi f. Beta is called the phase constant, and we'll have a lot more to say about the phase constant coming right up. The phase constant, the wavelength, and the frequency are related in terms of the following equations here. And you can find these equations any number of places, starting from high school level physics textbooks on up. The phase constant beta is 2 pi over lambda, where lambda is the wavelength of the wave. Beta can also be expressed in terms of the frequency omega and v. V is the velocity of propagation of the wave. Of course, you can also solve this top equation for the wavelength if you'd like. The wavelength would then be v over f, where I've used the fact that omega is 2 pi f there. So lambda is v over f, velocity over frequency. Also, of course, you can solve that equation for lambda to get lambda equal to 2 pi over beta. V, how about the velocity of propagation? Well, from the first equation, the velocity of propagation is omega over beta. The second equality here. Let me add a little word of warning here. The second equation there isn't always true. I also said that you can write the velocity of propagation as c, the speed of light, 3 times 10 to the 8th, divided by the square root of epsilon sub r, where that's the dielectric constant. That's the permittivity of the medium in which the wave is traveling. That's great as long as you've got some uniform medium where the whole wave exists. That's great as long as you can identify a single value of epsilon r to use in that equation. For a 2-wire transmission line, I can identify an epsilon r. It's the dielectric constant of the medium that surrounds the 2-wire line. In a coaxial line, yeah, again, I can identify epsilon r. You've got the outer conductor, you've got the inner conductor, and between the two is some dielectric. And epsilon r to use in that equation, that's epsilon r of the dielectric. How about in the microstrip? Epsilon r. What would I use? Let's check out that picture of a microstrip. I've got 2 possible epsilons I could use here. Some of the fields are in the substrate, where epsilon r might be, let's say, 2.25, like shown here. But some of the fields are up here in air. Epsilon r equals 1 for air. Question: I'm trying to find the velocity of the wave traveling down the microstrip transmission line. Some of it's above epsilon r1, some of it's below epsilon r 2.25. Which one do I use? Answer is neither. Actually, we're going to come up with a formula for the proper value of epsilon to use in this equation to give you the velocity of propagation in terms of the speed of light and this new value of epsilon called the effective dielectric constant, epsilon effective. I'll give you a formula later for that quantity for the special case of microstrip transmission lines. Okay, enough said for now, though. We'll see formulas for epsilon effective and how you change this equation for the microstrip coming up when we talk in particular about microstrip lines. But let's forget about microstrip for a moment and just think about the simpler types of transmission lines. Now, I'm going to use phasors since I've got a purely sinusoidal signal at a single fixed frequency of omega that I assume is given. There's the signal. It's a function of position and time. X and t appear in the expression for the voltage. And the phasor corresponding to that sinusoidally varying voltage is, as you would expect for a phasor, is not a function of time anymore. Just like in AC circuits, where phasors don't include a time dependence, phasors in this more general case of traveling waves, they don't depend on time either. But they still do depend on position. This is the big difference between phasors for AC circuits and phasors that we're going to make use of in this class, is that our phasors will include a time-dependent factor. The phasor will be given by the magnitude, same magnitude V0, 5 volts, let's say, times a exponential factor, e to the minus j beta x. You can write the phasor relationship for the phasor corresponding to a time-varying voltage. Every now and then I'll make use of this symbology to denote the phasor corresponding to a time-varying voltage. I do the same thing for a current and so on and so forth. Phasors are related to their corresponding time-varying quantities in exactly the same way they are in AC circuits, however. No difference between how you get the phasor from the time-varying quantity or how you get the time-varying quantity back from the phasor. Check out your circuits book. Your circuits book will tell you that in order to get a time-varying voltage out of a phasor voltage, you'd take the phasor voltage, you'd multiply by e to the j omega t, and then you take the real part. And that will give you the time-varying voltage corresponding to the phasor. We're doing the exact same operation here as we do in circuits 1. Only now our phasor depends on position. It's not just a complex number like it was in circuit theory. You can see, though, that performing this operation would give you the original time-varying quantity back again. I'd get this back starting with that phasor by performing this operation. Can everybody see that? For V of x, plug in V0 times e to the minus j beta x. So I'd have V0 e to the minus j beta x e to the j omega t. And I'm taking the real part of the result. Well, V0, that's like 5 volts or something. Pull that outside of the real operation. It's real to begin with. Then I need to take the real part of e to the minus j beta x times e to the j omega t. Well, combine the exponentials together to make it e to the j omega t minus beta x. All there up in one exponent. How would I find the real part of that? Anybody? The real part of e to the j something. How do you find the real part of that? Remember that identity way back from Calc 1, Calc 2, I guess? Well, Euler's identity, that's the one I'm looking for. E to the j x, let's call it, would be cosine x plus j sine x. E to the plus or minus jx is cosine x plus or minus jx. All right, we've got the real part of e to the j omega t minus beta x. Cosine of omega t minus beta x plus j sine omega t minus beta x. We want only the real part. What's the real part? Well, that's just the cosine part. The sine part was multiplied by a j. So the real part would give us exactly what we're looking for, cosine of omega t minus beta x. And we'd recover the original time-varying signal by performing this operation. Okay. So now let's start talking about applying phasers to, transmission lines. First thing is, on transmission lines, transmission lines are what's known by mathematicians as distributed systems. What that means is that the quantities of interest on a transmission line, and the quantities of interest I'm talking about are resistance, capacitance, inductance, and conductance, R, L, G, and C. Those are specified on a per unit basis. Let me put it this way. If a transmission line is connected to a source of 5 volts, and the transmission line is several meters long, and you connect it up to a load at the other end, and you know that source is 5 volts, you take a voltmeter and measure the voltage across the load. The voltage across the load for any real transmission line is not going to be 5 volts. The transmission line has some loss associated with it. It has some resistance associated with it. And by fiddling around with transmission lines, you'll find out that if you double the length of the transmission line, you get twice the voltage drop across the transmission line, and consequently even less voltage appearing across the load. If you half the value, the length of the transmission line, you get half the resistance associated with the transmission line, and you get a larger amount of voltage appearing across the load, less loss. So we think of resistance along with inductance and conductance and capacitance on transmission lines. Those are usually specified on a per meter basis. So, for instance, you might pull a transmission line off the shelf and read its data sheet, and it might tell you that the resistance of that transmission line is 0.1 ohms per meter. And you're going to use 3 meters of transmission line to connect your source with your load. How much resistance would you measure end to end just due to the transmission line? 0.3 ohms, because the transmission line has 0.1 ohms per meter of resistance, and you're using 3 meters. So take ohms per meter, multiply by meters, you get the number of ohms. And the same thing holds for the inductance associated with the transmission line, the conductance associated with it, and the capacitance, and so on. So that's why we call these transmission lines distributed circuits. It's like the resistance and all these other quantities are distributed like uniformly throughout the transmission line. You can't say, here is where the resistance of the transmission line is, at this particular point. No, it's all through the transmission line, sort of uniformly distributed. All right, now I want to do a circuit analysis on a piece of transmission line. What I'm going to do is I'm going to do a circuit analysis on a very short section of transmission line. If the section of transmission line that I do the circuit analysis on is small enough, I can say, well, for all intents and purposes, I could pinpoint this is the location where the resistance is, and this is the location where the capacitance is, and so on and so forth. Well, that's only an approximation. It still is distributed throughout that length of transmission line, even though the length of line is only 1 centimeter. But that approximation becomes exact in the limit as the length of the section of transmission line that I'm analyzing, as that length goes to 0. And I'll do that later. I'll take that limit. So let's imagine that we've got a short section of transmission line of length delta x. Then, if delta x is small enough, I could draw my circuit as shown on the top of the next page. Think about a 2-wire line, and I'm drawing the top wire and the bottom wire here. But this circuit works just as well for any other type of transmission line. It's just easiest to draw in the case of a two-wire line. What I'm doing here is I'm saying that the resistance that is in all actuality spread across the entire length delta x of that line, I'm lumping it all together in one location, right there, and putting a resistor in my circuit. What resistance value should I use? Well, remember, R is ohms per meter. I'm using a length delta x meters of line. So the appropriate value for that lumped resistor is R times delta x. R ohms per meter times delta x meters gives me the number of ohms. L, well, what value should I use for an inductor? L delta x. L is in henries per meter, delta x once again in meters. Here's the conductance. You can think of that as being current leakage from one conductor to the other conductor through the imperfect dielectric between those two conductors. And the value of the conductance, G times delta x. Also, there's a capacitance between the two conductors on the transmission line. And the appropriate value of the capacitance to use in this lumped circuit approximation would be C times delta x. Okay, now I'm going to do a simple circuit analysis of this circuit. Let's say that we have a voltage at these terminals of the short section. I'll call that V of x and t. Over here, I've got a voltage at the other terminals of the transmission line section of length delta x. I'll label that V of x plus delta x and t. It's at a location that if we called this location x and the line was of length delta x, of course, the location there would be x plus delta x. Similarly, we can talk about the current flowing into the section of transmission line. Once again, let's label it x and t for position and time. Current flowing out of the other end. Once again, we label it x plus delta x and t. And all I do is write Kirchhoff's voltage law and Kirchhoff's current law, solving for the voltage V of x plus delta x and t, and solving for the current I of x plus delta x and t. Okay. How about the voltage coming out? Well, the voltage at these terminals is going to be the voltage at these terminals minus any voltage drop between the two. Well, you could get a voltage drop across that resistor, you could get a voltage drop across that inductor, and then that's just a piece of wire. So the voltage at the output terminals is the voltage at the input terminals minus IR minus LdIdt. Those are the voltage drops across the resistor and the inductor. Only now it's not just Ri, it's R delta x times I. And it's not just L dIdt, it's L delta x dIdt. That's the first equation I've written there. Kirchhoff's voltage law. V of x and t minus the voltage drop across the resistor, R delta x, that's one quantity there, times I, minus L delta x times dIdt. That gives me the voltage at the output terminals. How about the current? Well, the current coming out is going to be the current coming in minus any current that goes through that branch minus any current that goes through that branch. So I of x plus delta x and t is going to be I of x minus G delta x times v. Remember, I is G times v. G delta x times v in our case. How about the current going through the capacitor? Current flowing through a capacitor is C dV dt, or in our case, C delta x dV dt. And just write that down. I of x and t minus G delta x times the voltage minus C delta x dV dt, taking away those two currents flowing through those two branches, is going to be the current left over that flows out through terminal 2, or the output current. All right, that's what I want, because now I can rearrange those equations, and I can do that trick I was telling you about earlier. I can take the limit as delta x goes to 0, and then that circuit approximation for that distributed transmission line circuit becomes an exact formulation in the limit as delta x goes to 0. We can see right now we're going to get derivatives with respect to x. Can everybody see that? Think about this. Subtract off v of x and t from both sides of that first equation. Also, divide by the delta x on both sides of the equation. And what do you end up with here on the right-hand side? V of x plus delta x and t minus v of x and t all over delta x. Take the limit as delta x goes to 0. Aha, mathematician would say. That's defined as the partial derivative of the voltage with respect to x. V of x plus delta x minus v of x all over delta x. Bingo. We've all seen that before. And you're left with r times I and L times di dt over on the other side of the equation. That's what I have written here. That's the first equation. Do the same thing with the second equation. Subtract I of x and t from both sides. Divide by delta x, once again. Take the limit as delta x goes to 0. You'll find you have the definition of the partial derivative of I with respect to x over here. And you have a couple of terms left over in terms of v and dv dt. There they are in the second equation. All right. Right now, these are very general equations for any time-varying voltages and currents. But now let's do what we were talking about. Let's simplify life for ourselves and use phasors. Let's assume that we're talking about sinusoidal variation for voltages and currents. The biggest simplification that happens when you make use of phasors is that differentiation with respect to time becomes nothing more than multiplication by a factor of j omega. And I write that in my symbolic notation as d by dt's become j omegas. And these two equations, which are called the telegraphist's equations, by the way. Those are those fancy telegraphist's equations I was telling you about earlier. Those two equations are simplified very nicely. First off, time derivatives vanish. They're just replaced by j omegas. There's the old time derivative on I, and there's the old time derivative on v. Now nothing more than multiplication by j omega. Also, that partial derivative stuff becomes total derivatives, because now we're talking about phasors, which are only functions of position. They're not functions of position and time any longer. We've taken out the time dependence by assuming phasors. So we have just plain old derivatives here. This is a pair of coupled first-order differential equations that we can solve quite easily. This is something that you'd find in a class on differential equations. The first thing to do with that pair of coupled equations is to uncouple them. The reason I call them coupled is because V and I appear in both. You don't have V alone in one and I alone in the other. Let's remedy that. Let's fiddle around with those equations and get one equation just in terms of V and another equation just in terms of I. And this is the way it always works. If you've got a pair of coupled first-order differential equations for two quantities, like V and I, you can always uncouple them, but you'll get two second-order equations for the uncoupled variables, V and I. Here's the form that the uncoupled equations will take. D squared V dx squared minus some constant times V is equal to 0. Same thing for I, an identical equation for I, where that something, that gamma, I call the complex propagation constant, and it's equal to the square root of that stuff that appeared multiplying R and I in the original equations, R plus j omega L and G plus j omega C. Does everybody see how I'd uncouple those two equations? Everybody see how I got the next pair of equations? Think about doing this. Think about this first equation. Take the derivative with respect to x, both sides of that equation. Differentiate both sides with respect to x. Okay, I'm going to get a d squared v dx squared over here. Here I'm going to get this constant times di dx. But the second equation tells me what di dx is right here in terms of v. So for the di dx that I end up with here, plug in this instead. What you'll end up with is d squared v dx squared is going to be equal to this term times that term times v of x. Or putting the v of x over onto the same side of the equation with the derivative, this is the form of the equation. You can do the same trick with the second equation. Differentiate it with respect to x. You'll end up with a dv dx term over on the right-hand side, but the first equation tells us what dv dx is in terms of I. Plug that first equation in, and you'll end up with an equation that looks just like this. Okay. That gamma thing, the complex propagation constant, it's complex, sure enough. I mean, you can tell it's got these real quantities, R and omega and L and G and C, but it's got J's occurring in it, J omega L and J omega C, and you're taking the square root of that complex thing, it's going to be a complex result. In general, the complex propagation constant, it's complex. You can say it has a real part and it has an imaginary part. And I'm going to call the real part alpha, and I'm going to call the imaginary part beta. Alpha, the real part, has a name. It's called the attenuation constant, and it has something to say about how signals attenuate as they travel down the transmission line. Beta is that phase constant that we saw when we were looking at those original formulas for traveling waves. That's the same beta that we have here. Now, I'm going to make one more simplification. This is a simplification that's often done. It's one that makes the math a lot easier. And that is, I'm going to make the simplification that we're working with a lossless transmission line where R and G, the two loss terms, resistance per unit length and conductance per unit length, are small enough that we can neglect them. Set them equal to 0. This is not as much of an approximation as you might think, because most transmission lines in use are pretty low loss. This approximation will give you darn good results, at least for the first cut. And generalizing the results we have here for lossy transmission lines is not too awful difficult. You'll find those results in many textbooks. You can refer to them if you'd like. And thirdly, the software. Well, software can deal with the general lossy case just as easily as the lossless case. So let's let the computer do the dirty work and start our design by considering lossless lines. Use that as a starting point for our computer design, and let the computer compute the differences between our pencil and paper lossless study and what the real world lossy line would give us. Well, one thing that happens is that this complex propagation constant becomes pure imaginary. That is, alpha, the attenuation constant, goes to 0. Imagine setting R and G equal to 0 here. So just ignore that term and ignore that term. What I'm saying is gamma, then, is pure imaginary. It's J something, no real part. You can see that because you've got J omega L multiplying J omega C underneath the square root. J times J is minus 1. And omega L and omega C are pure real. So we're taking the square root of a negative quantity. Well, the square root of a negative quantity is J times the square root of whatever's left over there underneath the square root sign. So we're going to get J times the square root of omega L times omega C, or omega squared times L times C. Or we're going to get J omega times the square root of L times C. Gamma is pure imaginary. That is to say that alpha is 0 and beta is the only part that survives, the J beta part. And this gives us another formula for beta, now in terms of the frequency of operation of the transmission line and the inductance and capacitance per unit meter of the transmission line. And remember, we had other formulas for beta. Here they are repeated. Those were our other formulas for beta in terms of wavelength and frequency and velocity of propagation. You can use this formula too and come up with some more formulas. Here's one, for instance. The velocity of propagation on the transmission line can be found in terms of those numbers you get off the data sheet, inductance and capacitance per unit length for the particular transmission line. Okay, now let's rewrite those equations from the top of the column, these ones, using the fact that gamma is just J beta. So here's what they look like now, using the fact that for a lossless line, gamma is J beta. A pair of equations, once again, identical equations. Those are equations, standard, homogeneous, linear, second order equations with constant coefficients that I'm sure you all are very familiar with. This is one of the easy cases that you studied in differential equations. Since they're second order equations, there are two independent solutions to each of those equations. And those two independent solutions, usually for these equations, they're called harmonic equations. Usually the solutions that are chosen are cosine and sine type solutions, trigonometric solutions. Those are the two independent solutions. But, of course, there are alternative solutions that we could use. How about complex exponentials? E to the j something or e to the minus j something. Those are the other pair of solutions that are equivalent to the cosine and sine solutions. I'm going to use the complex exponential solutions to those equations. So I'm going to write, let's say for instance, the general solution to that first equation for the phasor voltage. I'm going to write it, well, there's both of them. We'll write down general solutions for both equations. There are the most general possible solutions for V and I for those two equations. They're in terms of exponentials, e to the plus and minus j beta x, times constants, arbitrary magnitude constants. Here's one constant multiplying e to the minus j beta x. Here's another constant multiplying e to the plus j beta x. And I use a complicated notation. A mathematician would usually say C1 times this solution plus C2 times that solution. That's nothing more than C1 and C2 written in fancy notation. I call it V0 plus and V0 minus because we're going to find that the solution that has e to the minus j beta x dependence, that solution corresponds to a traveling wave traveling in the plus x direction. Whereas the solution that has an x dependence e to the plus j beta x, that corresponds to a traveling wave traveling backward on the transmission line, traveling in the minus x direction. So I call its magnitude coefficient, I call that V0 minus for the backward traveling wave solution, or the solution traveling in the minus x direction. Note that very carefully. The positive traveling wave solution has the minus j beta x dependence. The backward solution traveling in the minus x direction has the plus j beta x dependence. Same thing for the solution for the current in terms of arbitrary magnitude coefficients I0 plus and I0 minus for the two independent solutions to the differential equation. How do you pin down the values of, let's say, V0 plus and V0 minus, and I0 plus and I0 minus? Well, that depends on boundary conditions or initial conditions. Remember, you always got to have those in order to take the general solution and pin it down to a particular solution. Okay, well, we can start fiddling around with those solutions and get some relationships between those magnitude coefficients. One thing I can do is take these two solutions and substitute back into the original telegraphist's equations in phasor form. I'm talking about here, these equations. Remember, these are the telegraphist's equations. Here are the telegraphist's equations in phasor form. Plug these solutions into the telegraphist's equations in phasor form, and you can find these relationships must exist between the magnitude coefficients. You'll find out that V0 plus over I0 plus is equal to a constant, and so is the negative of V0 minus over I0 minus. The reason for the minus sign is because the ratio of those quantities are actually negatives of one another. But they're the same constant. They're the same constant. And I define that constant to be, symbolically, I call it Z0. Z0 is a very important constant. We'll be seeing that Z0 appearing over and over and over again. We give it the name characteristic impedance. That is the characteristic impedance that you often hear talked about with regard to transmission lines. in general for the lossy line, Z0 from the original telegraphist's equation for the lossy line. You can find Z0 is equal to square root of R plus j omega L over G plus j omega C. For the lossless line, easy enough, set R and G equal to 0 in that equation. So these two terms disappear. Then you get just j omega L divided by j omega C under the square root sign. But the j omegas cancel out. So you really have just L over C under the square root sign. And there it is, the very simple form that the characteristic impedance takes for the lossless line. All right, now, the characteristic impedance of the transmission line is a very, very important quantity. However, it's also important to make sure that you interpret that quantity correctly. 50 ohm lines, that's the main type of transmission line that's used in practice. Sometimes you see 75 ohm lines. Very seldom you'll see 150 ohm lines. 50 ohm lines is almost the universal value for the characteristic impedance of transmission lines. It's a standard. Okay, you give a technician a 50 ohm transmission line and tell him, here's a 50 ohm transmission line. And the guy will scratch his head and say, 50 ohms, okay, what does that mean? Where do I measure the 50 ohms? Can I connect an ohm meter between the two ends of the transmission line and measure 50 ohms? No. Can I take an ohm meter and connect it between the outer conductor and the inner conductor at one end of a transmission line, like a coax line, and measure 50 ohms? No. The tech is going to say, well, why do you call this a 50 ohm line? Where's the 50 ohms? The best answer you can give is this. If you had a voltage and current wave traveling in one direction and only one direction down that line, and you took the ratio of the voltage to the current in that one wave traveling in one direction, the ratio of V to I would be 50. Or if it was traveling in one direction and the other direction down the transmission line, V divided by I would be 50 at every point on the line. However, you take a source, you connect a load, and you've got forward traveling waves traveling down the line. You can have backward traveling waves traveling back up the line because of reflections off of the load. And you try to measure the total voltage divided by the total current at any point on the line, V divided by I. All bets are off. It's not 50. 50 is the value only in that one particular case of only considering forward waves of voltage and current and taking their ratio, or only backward waves and taking their ratio. If you've got the two combined at the same time, the ratio of total waves is no longer 50. Yeah, the forward waves by themselves have a ratio of 50, and the backward waves by themselves do. But combine them together, you no longer have that simple relationship. Well, in any event, let's see what we can do to simplify those general expressions for voltage and current, making use of this relationship. Here's how I'm going to use it. I'm going to say that I0 plus can be written as V0 plus divided by Z0. Similarly, I0 minus can be written as V0 minus times Z0 with a minus sign. And make those substitutions for I0 plus and I0 minus based on this relationship. So, I can eliminate I0 plus and I0 minus in my expressions for V and I by making use of the relationship to the characteristic impedance. What used to be an I0 plus here now becomes V0 plus over Z0. And what used to be a I minus, I0 minus, now becomes a negative V0 minus divided by Z0. Factor out the 1 over Z0 and write it as follows. Now we've got just 2 of our 4 arbitrary amplitude coefficients left in the expressions. Now, let's stop right here and take a look at those 2 equations and see what they tell us. One thing I note immediately is we have a plus sign between the forward traveling wave term and the backward traveling wave term for voltages. But I have a minus sign between the forward traveling wave term and the backward traveling wave term for currents. This is an interesting thing that occurs on transmission lines. Amplitude of forward and backward current waves are forward and backward voltage waves divided by Z0. Sure enough, I is equal to V divided by Z. Amps is equal to volts divided by ohms. That still works. But forward and backward voltage waves add together. There's a plus sign here. Forward and backward current waves subtract from one another. This is a very interesting property of transmission lines. And let me turn real fast to Elmo. Just make you a little sketch to try to reinforce this fact. Here's my nifty little transmission line. Okay, on one end of the line, there's a forward traveling voltage wave, positive polarity, negative polarity measured between the 2 wires of the 2-wire line. Here's a forward traveling current wave. That's what those squiggly arrows are supposed to represent to you. Current traveling in one direction on the upper conductor and the other direction on the lower conductor. Let's think about voltage wave traveling in the opposite direction. And the polarity I'm going to use is the polarity shown here. And let's think about a backward traveling current wave. And once again, upper conductor has current flowing in the direction of propagation. The lower conductor has the return current. Those 2 waves are moving in from either end of the transmission line. Well, check out the polarities of the voltages. They're the same. If the forward traveling voltage wave has a magnitude coefficient of 5 volts, a peak value of 5 volts for that sinusoid, and the backward traveling voltage wave has a peak value of 2 volts, let's say, what's the peak value you could possibly have at any point on the line while the 2 voltages are there together? Well, since they have the same polarity, the 2 voltages would add together, 2 plus 5, 7 volts. How about the currents? Check it out. They're in opposite directions, defined in opposite directions on both of those conductors. So, if you wanted to know the current, where those forward and backward current waves come together, I guess the current here is going to subtract off of the current there, giving you an overall current value that's going to be the difference between the forward traveling wave current and the backward traveling wave current. So that's a sort of a physical picture that goes along with the equations. The equations tell us that this is the result. And this is one way to remember it and to perhaps understand the difference between voltages and currents traveling in opposite directions on the line. Now, this difference between the way forward and backward voltages and forward and backward currents interfere with one another, constructive interference for voltages, destructive interference for currents, that's the whole reason why transmission lines behave differently than regular circuits to begin with. If only that minus sign wasn't there, we wouldn't have to worry about circuit analysis for transmission lines. It would be no different than circuit analysis for regular low-frequency AC circuits. You wouldn't have to use Smith charts. Things would be trivial. Well, they're not trivial, thanks to that minus sign there. Okay, let's do something useful with our line. Let's stop thinking about these lines connected to nothing on each end. Let's hook up a load at one end of the line. We're still working with phasors, and we will be for the remainder of the semester. So we'll talk about impedances, Z. So I'll call the impedance of the load Z sub L. It could be a resistor, R. It could be an inductor, J omega L. It could be a capacitor, minus 1 over J omega, minus of J, 1 over omega C. I'm going to imagine we have a forward traveling voltage wave traveling from these terminals, which I'm going to think of as the input terminals, of a section of transmission line of length script L with that load ZL at the other end. Well, if the line has length script L, that means that if I said that this was x equals 0, this was my origin of coordinates for the variable x, and if I said that this was a forward traveling voltage wave traveling in the plus x direction, then I guess these terminals here would have to be at x equals minus L to make the line of length L. So x equals minus L at the input terminals, x equals 0 at the load terminals. I could, of course, have chosen this location to be x equals 0, then that location would have been x equals L. I'm shifting those coordinates. The reason for using the shifted coordinates with x equals 0 at the load is because I'm going to be doing a little bit of circuit analysis at the load, and it's a lot easier if x equals 0 at the load. It just leads to easier equations, simpler equations. Let's also assume that the transmission line is given. It's known. We pulled it off the shelf. We know its characteristic impedance, 50 ohms. And we know the phase constant. We know the frequency omega, and we know L and C, and beta is just omega times the square root of L times C. So those two quantities are given for the transmission line. Now, if there is, excuse me once again, if there is a forward traveling voltage wave traveling down this transmission line with this termination of ZL, then in general there's going to be a reflected voltage wave traveling back up the transmission line, voltage reflected off of the load. That is to say, you put a source over here, a 5-volt source, and you want to know how much power is absorbed by that load. Usually you'd say something like V squared over R, or magnitude V squared over real part of Z sub L, or whatever. You'll find out that no, not all that power from the source is actually absorbed by the load. In most cases, some of that power is reflected off of the load to form a wave traveling back up the transmission line in the minus x direction. And we're going to find out how much of that incident wave is reflected off of the load. Okay, let's apply Ohm's law at the load terminals. The voltage at the load terminals, as far as the transmission line is concerned, is given by taking the equation for the voltage on a transmission line and setting x equal to 0. Let's see, is that on this same page? Here we go, yeah. Here's V of x in general on a transmission line, and we want to know the particular value of V at x equals 0. That's where our load is. So V of 0 is given just by setting x equal to 0. We get V0 plus e to the minus j0 plus V0 minus times e to the plus j0. But e to the 0 is equal to e to the j0. E to the 0 is 1. So both of those exponential factors are 1. And we end up with simply V0 plus times 1 plus V0 minus times 1 from the transmission line equation. How about the voltage here in terms of Ohm's law? Ohm's law tells me that V is equal to IR, or for phasors, V is equal to IZ. Well, let's use the expression for the current at x equals 0 from the transmission line equation. And Z, here it is, Z sub L, that's I from the expression for currents on transmission line at x equals 0. There's I in general. Set x equals 0. That factor becomes 1. That factor becomes 1. I is equal to 1 over Z0, V0 plus minus V0 minus. I is equal to 1 over Z0, V0 plus, where am I? Too far down. See if I can control this darn thing. 1 over Z0, V0 plus minus V0 minus. That's I times ZL. V is equal to IZ. Okay, well, those voltages have to be the same. They're both voltages at the load terminals. That's an equation that we can solve. I'm going to solve that equation, single equation with two unknowns. The unknowns being the amplitude coefficient V0 plus for the forward wave and V0 minus for the backward wave. I'm going to solve that equation first for the ratio, V0 minus divided by V0 plus. So solve that equation for the ratio, V0 minus to V0 plus, and you'll find that that equation will give you the following expression for that ratio. It will give you the ratio, ZL minus Z0 over ZL plus Z0. That ought to be a familiar one to all of you. This is another famous, well-known transmission line quantity which we call the load reflection coefficient. Or for short, I'll often call it just reflection coefficient, denoted gamma 0, or sometimes I forget to put the 0 there. The book likes to put a 0 for the load. Gamma 0, gamma 0. That's what we mean by V0 minus over V0 plus. Then we could, of course, solve for V0 minus in terms of V0 plus using that equation. V0 minus would be gamma 0 times V0 plus, and let's plug that now into the pair of equations for V and I from the previous column. So for V0 minus, for I and Z here, let's use V0 minus being equal to gamma 0 times V0 plus. That means there's only going to be one unknown amplitude coefficient left in my equations for V and I. That one unknown amplitude coefficient that's left is V0 plus. Everything else is expressed in terms of V0 plus. For V of x, we had V0 plus times e to the minus j beta x. There it is. We also had V0 minus times e to the plus j beta x. But V0 minus is V0 plus times gamma 0. We have a common factor of V0 plus, so factor that outside. What's left over in the backward traveling wave term is the gamma 0. Same thing for the expression for current. Forward traveling wave current, write it the same way it was in the previous column, but for the backward traveling wave current, it had a V0 minus. Plug in V0 minus is gamma 0 times V0 plus. Factor out the common V0 plus from both terms, and you're left with, once again, a factor of gamma 0 multiplying the backward traveling wave current term along with its minus sign, showing us that forward and backward currents subtract from one another. All right, now, I said at the top of this column when we looked at that drawing that if you connect up a source here to some transmission line with given parameters and you connect a load up to the other end, in general you're going to have voltage waves and current waves traveling in both directions. You're not only going to have voltage and current traveling from the source to the load, but some of the voltage and some of the current is going to be reflected off that load, travel back up the transmission line from load to source, in general. There is one particular case where there's going to be no reflected voltage and current. That is when the load has a particular value. What particular value would I use for ZL to make sure that there is no reflected voltage or reflected current? Yeah, right. It's called a matched load. A matched load is what would do it for us. That's where ZL is chosen to be equal to Z0. That is, if you've got a 50 ohm line, if Z0 is 50 ohm, the best thing to do, and something we're going to be shooting for a lot in this class, is to match the load to the line. That is, use a load that's 50 ohms also. If the line's a 50 ohm line, use a 50 ohm load. Because nice things happen. If ZL is equal to Z0, then this reflection coefficient with a ZL minus Z0 in its numerator is nothing. It's 0. And looking at these equations, you can see that if this term disappears and that term disappears, we have only forward traveling wave terms for voltage and current. Physically, what that means is any signal that you put on a transmission line that has a matched load, any signal that you put on that line traveling from the source towards the load, any signal is going to be completely absorbed by the load. None of it is going to be reflected off of the load back up toward the source. This term, this backward traveling voltage wave term, and the corresponding backward traveling current wave term, they vanish. This is a very nice situation to have happen. This is the situation that will lead to maximum power transfer. If the source is producing 5 watts of power and you've got a matched load and you've got a lossless line, all 5 watts are going to be absorbed by the load. If the load's not matched, if you've got a 50 ohm line and your load is 50 plus J10 as an inductive portion, or it's 30 plus J0, or any other value, anything but 50 ohms, then the reflection coefficient is non-zero. That means you're going to have a reflected voltage wave, a reflected current wave, a portion of that 5 watts that you launch down the line towards the load, a portion, and you can tell what portion by computing the magnitude of the reflection coefficient, a percentage is going to be bounced right back off the load, back up the line toward the source. Not a great thing to have happen in a lot of circumstances. Efficiency is one reason. Other reasons might be that having 5 watts traveling from the source down to the load and having 1 watt being reflected back up the line into the output terminals of the source could damage the source, maybe even burn it out. So for a lot of reasons, we often shoot for a matched condition for our loads. And we're going to be talking about special networks that you can create to take a load that's not necessarily a 50 ohm load and connect it up to a 50 ohm line using a matching network in between the load and the line that will make the load, which isn't 50 ohms, appear at the terminals of the matching network to be a matched load for maximum power transfer. We'll talk a lot about that coming up. All right. Now that we have nice equations for voltage and current, we can start talking about impedance. Impedance being the ratio of voltage to current. By the way, this is all the further I can bring it as far as my general equations for voltage and current. There still is one unknown left, V0 plus. It appears in both equations for V and I on the line. You can't get rid of it until you tell me exactly how far you turn up the source connected to the input terminals of this transmission line circuit. So the magnitude of V0 plus depends on the power that your source is putting out, which we're going to take as a quantity that will be specified differently in each different problem. But taking the ratio of the two, taking the ratio of V to I to define an impedance causes that unknown amplitude V0 plus to disappear. Because remember, V0 plus multiplied V and multiplied I, so it cancels out in numerator and denominator. So simply take those two expressions I have on the previous page and divide the two of them, and you get this as the result. By suitable manipulation, making use of Euler's identity, this expression for the impedance at any location x, and you can plug in any x you want to find the impedance at different points on the line, this expression in terms of complex exponentials can be converted to a trigonometric form using the fact that e to the j anything is cosine of that thing plus j sine of that thing, plus or minus, depending on whether it's e to the plus or minus j something. So use Euler's identity on the exponentials in the numerator and in the denominator, expand it all out in terms of sines and cosines. The other thing I've done going from this term to that equality is I also plugged in the expression for gamma 0 and simplified things out there. Gamma 0, if you recall, ZL minus Z0 over ZL plus Z0. So I'll plug that in as well and do a bunch of manipulation. You'll end up with sines and cosines, and you can divide sine by cosine to get tangent. And there we have an expression for the impedance at any point on the line in terms of the tangent function rather than the complex exponential. Okay, this is a formula for the ratio of total voltage to total current at any point on the line. This is what I was talking about earlier when I said that you're giving that piece of transmission line to the tech and telling him it's a 50 ohm line and he's wondering what you mean by 50 ohms. And I said, you can't even say to him that if he measured the ratio of the voltage to the current at any point on the line, he'd get 50 ohms. No. If he measured the voltage to current ratio at any point on the line, that's what he'd get. V divided by I. And it changes depending on exactly where he makes the measurement. What location on the line. It's only when you're talking about a forward traveling wave all by itself or a backward traveling wave all by itself that you get 50 ohms. You can actually see that from this equation. Imagine that you have only a forward traveling wave on the line. That means that this term in the numerator isn't there and the second term in the denominator isn't there. So get rid of those two terms. You have this common e to the minus j beta x in both numerator and denominator. You can cancel those two terms and you'll see that z of x is z0, 50 ohms, at any x. Doesn't even depend on x. If there's no backward traveling wave, and you're only considering forward traveling waves. Or, on the other hand, consider only backward traveling waves. The ones with the e to the minus j beta x disappear. You have only the ones with the plus j beta x. The e to the plus j beta x, numerator and denominator cancel, and once again you'll get just plain old z0, 50 ohms. But not in general. Not when you have forward and backward waves together. Much more complicated expression for the ratio of voltage to current. However, there is one special case of this formula that's of most interest to us. It's a formula that is called the formula for the input impedance on the transmission line. And the input impedance on the transmission line has its own symbol associated with it. We call it Zn. Zn is the impedance at the source terminals, or at the input terminals of that section of transmission line of length L, characteristic impedance Z0, with a load impedance ZL. All I do to get my formula for Zn out of that first formula for Z of x is plug in what x is equal to at the input terminals. So take that formula at the top of the screen and plug in the particular value of x at the input terminals. And remember, we're using that strange shifted coordinate system where at the input terminals x is equal to minus L. So plug in x equals minus L here, and you'll get what I call the formula for the input impedance. Zn then, it'll be a formula in terms of L, the length of the line. It's given by taking this formula for Z as a function of x and choosing the particular value of x equals minus L, and put in minus L here and minus L there. Tangent function is an odd function. Tangent of the negative of something is just minus of the tangent of that quantity. So the minus signs here turn into plus signs. And x is replaced by minus L, so we get an L in the argument of the tangent function. Okay, what do I mean by Zn of L? Oops, wrong way. Let's look at the original circuit. There we go. Zn is the input impedance at that arrow there of this section of circuit, section of transmission line of length L terminated by load ZL. Let's say you have a 50 ohm line and a load that's 20 minus J10. Plug in that value for Z0 and that value for ZL. Tell me how long the line is. Tell me what the phase constant of the line is as well. And then I can use that formula to tell you what impedance you'd see at these input terminals of that section of transmission line. And of course, by the input impedance there, what that means for the circuit is that if this section of transmission line with this load impedance was connected up to another portion of circuit over here, I could replace the transmission line and the load by the input impedance, Zn, by a single impedance, Zn, right there. And it would not change the operation of the rest of the circuit that's connected up to those terminals. So Zn is the impedance looking into those terminals. Okay, a couple words of warning when using this formula. Make sure you're in radian mode when you do calculations using this formula, because beta L has units of radians. Beta is 2 pi divided by lambda. That 2 pi ought to be a hint that you're working with radians. Actually, beta L is a quantity in itself. Beta L is going to pop up over and over and over in our calculations. It's convenient to give it a name. We call beta L the electrical length of the line. L is the length of the line in meters. Beta L is the electrical length of the line in radians. The electrical length of the line is actually the more meaningful quantity of the two. And I'll tell you why that is in just a moment. First of all, I say beta L, the electrical length, is a sort of a measure of how long the line is compared to a wavelength. And you can see this as follows. Beta L. Well, beta, from one of our formulas previously, beta is 2 pi over lambda. So beta L is 2 pi over lambda times L. Well, let's write that by factoring out that 2 pi and writing it as 2 pi L over lambda. L over lambda, that's the length in wavelengths. If L is 2 meters and lambda is 1 meter, then L over lambda is 2. That tells me that the length of the line is twice a wavelength, 2 wavelengths long. So beta L is the length of the line in wavelengths times a factor of 2 pi, because it's in radians. It's the length of the line in wavelengths. We call it the electrical length. Now, this is something that I see over and over and over in the results that students give me in computations, especially for my graduate students who are doing a lot of computations and plots and so on and so forth, or experiments. And they say, okay, Dr. Bagby, here's the plot for the transmission line that was 1.5 meters long. And these are the results that I got from the measurement or from the calculation. Do these results look reasonable to you? And I have to throw up my hands and say, I have no idea. 1.5 meters makes absolutely no sense to me. How many wavelengths long was that transmission line? If we're talking about operating at 60 hertz, 1.5 wavelengths is negligible wavelength, negligible length. But at 300 megahertz, 1.5 wavelengths is maybe it's a tenth of 1.5 meters. Maybe that's a tenth of a wavelength. Whereas at 3 gigahertz, 1.5 meters may be 3 wavelengths long. It's the number of wavelengths long that section of transmission line is that's going to determine whether the results I see make sense or not. So I always tell them, don't tell me how many meters or centimeters or millimeters long your transmission line is. Tell me the electrical length. Tell me what matters. Tell me how long it is relative to the wavelength. And that's the way it works out in the formulas too. It doesn't matter how long the section of line is. Absolute in meters, that's not what matters. What matters is the length relative to a wavelength when you're trying to figure out what the input impedance is. Okay, so I'm going to be talking about some specific examples here, but I'm going to talk about based on things like how many wavelengths long the line is and things of that nature, not how many meters long the line is. Okay, well, we already talked about this first example, the matched transmission line section. Turns out that for a matched transmission line, that is to say, a transmission line circuit where the load impedance is chosen to be equal to 50 ohms or equal to the characteristic impedance, then that formula up there for Z in is always going to give you 50 ohms as a result. That means it does not matter how long the piece of transmission line is if the load is equal to the characteristic impedance. No matter how long the line is or how short the line is, the input impedance is going to be 50 ohms always. You can see that in this formula by setting ZL equal to Z0. If ZL equals Z0 in the formula for input impedance, then we've got Z0 plus JZ0 tan beta L over Z0 plus JZ0 tan beta L. Numerator and denominator are equal, no matter what L is. So that term and that term cancel. Z in is just Z0 for a matched line. This is another nice thing about having the load matched to the characteristic impedance of the line, is that you don't have to worry about how long the line is. You're always going to see 50 ohms as the input impedance, or characteristic impedance of the line as the input impedance. All right, let's take a look at a couple of other extreme conditions. Let's say that we either had a short circuit or an open circuit on the end of the transmission line. That is to say, we leave the two terminals of the transmission line at output We just leave them alone. We don't put any load at all there. Open circuit the transmission line. Then the load impedance is actually infinite impedance. No current flows whatsoever. On the other hand, short circuit, well, that means just take a piece of wire and short circuit the output terminals. Nice things happen to the formula for Zn in both cases. Either put in ZL of 0 or put in a ZL that goes to infinity in this formula. If ZL is equal to 0, then this term and this term are not with us. This Z0 in the numerator cancels that Z0 in the denominator. And all we have is Zn is equal to JZ0 tan beta L. That's for the short circuit. For the open circuit, let ZL be something really, really big, and let ZL actually in the limit go to infinity. What that means is that in the numerator, the term here involving ZL completely swamps out the other term. This term can be neglected because ZL is so large. We're actually going to take the limit as ZL goes to infinity. Similarly, in the denominator, this term with the ZL is very, very big compared to that term. Ignore that term and just consider that term. We're actually going to take the limit as ZL goes to infinity. What happens here? That term we're ignoring, that term we're ignoring. We've got a ZL in numerator and denominator, nicely enough, cancel, leaving Z0 times 1 over J tan beta L. Well, let's see, 1 over J minus J in the numerator. 1 over tangent, cotangent. And so there's the corresponding formula for open circuit termination. Okay, one thing to make note of here, interesting, is that for a short circuit termination and for an open circuit termination, the input impedance, it does depend on the length of the line. Okay, so just because you have a short circuit at the output terminals of your transmission lines does not mean that you're going to see a short circuit looking into the input terminals. Actually, you'll see just about anything but. You will see an impedance for the short circuit termination that, number one, is going to be pure imaginary, multiplied by J, always purely reactive input impedance. And it's Z0 times a tangent function, and that tangent function is a pretty wild-looking function. Remember, the tangent function goes from minus infinity to plus infinity periodically with a period of pi for its argument, and so on and so forth. So what I'm going to do next time is I'll take up with some sketches of what those functions for input impedance look like for open circuit and short circuit terminations. Okay, we have a homework set due today. Make sure you get that up to me. Within the next couple of hours, I will have solutions posted on Blackboard. So by later this afternoon, visit Blackboard, get those solutions. Also get class notes for Chapter 2. We'll be getting into. Was that right? Thursday, you're right. I'm sorry. It was last time I did it. Okay, Thursday. I'm sorry about that. Yes. I wasn't here. Yeah, okay. Sorry about that. But do get class notes for Chapter 2. We'll get into those next time. False alarm, guys.